Hello scholars, welcome. Mr. Hinkle here. Today we're getting into the scientific method. So the scientific method is a system of analysis. It's how we complete science. It's how we ask questions and conduct experiments and analyze our results to develop these theories that explain the natural world around us. It's a little bit more complex than that, so let's get into it. Objective of today's lecture is to introduce the scientific method and its key components. Also, I really want to discern the difference between what a hypothesis and a theory is in relation to the scientific method, not in relation to how we use it in colloquial terms in our everyday lives. It's actually completely backwards. So I'll get into that here soon. The scientific method, by definition, is a systematic, logical approach used by scientists to investigate natural phenomena. This is what science does. It seeks to understand with objective observations, free from bias, observing natural patterns in the world so that we can learn how our universe works. It involves a series of steps that guide the process of inquiry, experimentation, and analysis. The scientific method, there's the good old tried and true 5-step way, and I'll get into it here soon, but it's more complex than that. So we can add as many layers of complexity as we want. So I'm going to offer and introduce different layers of complexity as we go. But it always starts with an observation. An observation, we see something happening in the world, and we're curious. From there we question, ask a question, identify a problem, then look to the research, search for existing answers or solutions to develop a hypothesis. A hypothesis is an educated guess on how some natural phenomenon exists or works in the world based on the research that we have learned. So, hypothesis is a formulated question or idea about how something works. Great. Thank you for bearing with me while I write all that text. First thing we do, formulate a question, observing a problem, developing a hypothesis, and then apply objective experimentation and observation. So we design some kind of experiment to test the hypothesis. From the experiment, analyze collected data, interpret those results. Those results can lead to devising an evidence-based theory, and once we have that, submit findings to peer review and/or publication. It's an ongoing process that has a cyclical nature. And so let's go through each of the components one by one. So observe a problem or research question. It all begins with observations. These giant blocks of rocks, researcher for scale, are the Titus Canyon mega breccia. So here is a geology problem. How did these car-sized blocks of rock get suspended in this matrix within this canyon? How are these big blocks of rock suspended in other rock? We don't know. It's not well understood. There is the question. So go to the literature. See what's out there in the body of research, what other people have been studying. From there, develop experiments, maybe in the lab, maybe out in the fields. What the agreed solution to this question is, skipping ahead, is that these were blocks of rock inside of a cavern, and the cavern collapsed in on itself, and so those giant blocks of rocks were suspended in the sediment surrounding the bigger pieces. Okay, great. Problem solved. Well, as far as we know, because the core tenet of science is that all ideas are falsifiable. And we don't prove hypotheses correct, we fail to prove them wrong. So we have an idea, a hypothesis, which leads to, so this hypothesis, a specific and falsifiable statement that predicts the outcome of an experiment. A good hypothesis is specific, it's clear, and it can be tested. And often when we're conducting science, we generate multiple hypotheses. A bunch of them get proved wrong. The ones that don't get proved wrong are subject to further investigation, to further analysis, and to further testing. So, make observations. Background research, step 1. Develop a hypothesis, step 2. Conduct an experiment that supports or refutes your hypothesis. Now, again, it didn't say that proves your hypothesis right. Really what we're looking at is our hypothesis can be rejected, refuted, and in absence of rejecting our hypothesis, it actually supports it. So we can complete these experiments in the field, in the lab, and gather data, objective observations or empirical data. A hypothesis is not proven right, but failed to be proven wrong. I've talked about that multiple times. A hypothesis must be clear, specific, and falsifiable. If the hypothesis is proven false, we throw it out. If we can't prove it false, we support it, saying that it has survived the rigorous experimental testing. Rejected hypotheses can be revised and tested again, so on and so forth as time goes on. So, if the hypothesis then is supported, is supported, does not get rejected, fails to get rejected, that provides evidence, and these results can be submitted to a peer-reviewed journal. This is the gold standard for communicating scientific findings. Before it's published, not any scientist can just go out and say, hey, I'm going to publish my research, but they have to write it in a formal research paper, submit it to a journal publication. It undergoes peer review. So at least three experts in that field, look at it, try and rip it apart, say that this actually doesn't hold up, but if it does hold up, meaning that their science is good science and it meets the expectations and the understanding of the surrounding science around it, then it can be published in reputable journals, Science, Nature, Geology, The Lancet, so on and so forth. The science isn't done then. At that point, the study can be replicated. It's out there to the world, so any scientist can say, oh, I see the experiment that you did. Let me do that experiment and see if I can replicate your results. The more that happens, the further confirmation, the more reliable the results become. And then the hypothesis is elevated to a scientific theory. When subject to repeated tests of falsifiability have occurred and documented confirmation of the experiments from multiple researchers takes place, we get a theory, which is a widely supported belief with evidence. This is the big part. With evidence. Okay. So, in pop culture, in the movies, in podcasts, in TV, pretty much anywhere, often you hear a person, random person, non-scientists go, I have a theory. I think this is how it happens. Or again, oh, will you tell me your theory on that? But in science, a statement is not a theory. Never. A statement about an idea about how something happened, that would be more closely related to a hypothesis. A scientific theory. And so this is important to know. If your friend says, I have a theory about why you're always late. Oh, do you now? Well, I'd love to hear that. That's not actually a theory. I mean, it's an idea, it's a guess, it's a statement about an opinion. But a scientific theory is a widely supported belief with evidence, and the evidence comes from rigorous testing and experimentation of multiple hypotheses that happens over time by independent researchers to confirm those results and help us to believe in the reliability of them. So this well-substantiated explanation of some aspect of the natural world. It is the best of our understanding. But even theories are falsifiable. This is the tenet of science. We never say, my theory is absolutely true, because nobody could prove it wrong. It doesn't work like that. At any point, a theory can be proven wrong with new evidence, new technology, new understanding. This is the beauty of science. It's ongoing, it's cyclical, it never ends. So truth is probable, the most likely truth, based on available observations, but new observations can yield scientific progress. Our example here is the impact theory for dinosaur extinction. We have lots of lines of evidence: a layer of iridium that surrounds the globe, a giant impact crater off the Yucatan Peninsula, the Chicxulub crater. But no one was around 65 million years ago, so we will never know how the dinosaurs went extinct. But we have lots of lines of evidence that multiple researchers have agreed this is how the dinosaurs went extinct. The scientific method provides a structured approach to asking questions about our universe. It's always provisional, and it's subject to change as we get new evidence. Right now, the new evidence for the formation of galaxies in our solar system is coming from the James Webb Space Telescope, the highest powered space telescope that launched in 2021 is now out there sending us new information about deep space. Science iterates, which means it happens over and over and over again. And this iteration of the scientific method leads us to technological advances, which then further iterates to help us understand more about our universe. So the scientific method, it is a process of inquiry that helps us. It guides how we conduct science. It helps us discover how our natural world works through inquiry, experimentation, and analysis. And we have, within the scientific method, we have ideas that generate hypotheses, a formulated question or idea about how something works, that undergo rigorous experimentation, multiple independent researchers, to elevate this idea into a widely supported belief that's supported with evidence, supported widely through the scientific community. So this is a tool. The scientific method is a tool for how science is conducted and completed, and it is ongoing, it is cyclical, it is repeatable, verifiable, and it's based on the tenet that all hypotheses or theories are falsifiable. Thank you to science for helping us understand how our world works, and thank you to the scientific method for laying out a pathway to complete science. And thank you for your attention. I'll see you again.